everybody. This is our last video lecture before the final exam. Don't forget your final exam is on Wednesday, May 6th. I think it's from 12 to 2 in this very room. Hi, Audra.
Hi.
I would like to have a study session for this final, and I'd like to get it started a little earlier. Than being very close to Wednesday. In particular, I doubt. In particular, we have in particular, I like to do it on Sunday. So that's what I got. Sunday evening. So I'm thinking about if people would like to, we have study sessions. Let's say Sunday from 6 until 8 in this very room. You know what? Let's don't make it in this room. I don't even know if the library is open.
The library will be open.
It's supposed to be open till 12. Okay, then we do it in this very room. I'll get the security to open this up, open the room up, and we'll do it. Sunday from 6 to 8. That's what I'll say.
Will you record it?
Yes, I will record it. Okay, so the next thing I want to do is pass back some graded material. So here are your test tubes. John's not here, Chuck's not here, Audrey. Dalvin's here. And so for those of you who are here, that's what I saw. You make sure that I added the points correctly. And if you'd like to ask a question about something, I'd be happy to go over it with you here about the test. And I want to remind you of something. What I want to remind you of is that if you do better on your final exam than your lowest graded material, I will replace what you did on your lowest graded material, percentage-wise, by what you do on the final exam. So let's say you made a 52 as your lowest graded material. I don't know if anybody made a 52. Let's say somebody made a 52, and on the final exam, they make an 81%. Then where there was a 52, it gets replaced with 81. Okay, so that's what I say. So still chance to really improve your scores if you do well on the final. It's hard to do well on the final, though, because it's comprehensive. But what I'm going to do is pretty much what I said here on this final exam study sheet. The final exam study sheet is available online. It was sent out through email. And so I'm going to ask you, it's going to have the final exam is going to be of the same format of the other two exams. The first question is going to be about listing definitions. And it'll be main definitions that we've had, mostly, but everything's fair game in terms of definitions. And then the next questions will be named theorems. And listen, when I say I'm going to have some definitions and it's going to have the same format, it is this final exam is going to have the same format of the other two tests. It is, but it's going to have a lot more questions. So there won't be 4 definitions. There'll be a lot more than 4 definitions. But if there was an important definition, it's going to be there. Important meaning there was a lot of material that we covered that involved that definition. So there is no way I'm giving you a final exam that doesn't have what's the definition of the limit of a function. That's going to be there. There's no way I'm going to give you a final exam that doesn't have what's the definition of continuity at a point. It's going to be there. What's a Cauchy sequence? It's going to be there. Okay? It's going to be there. So, what does it mean for a sequence to converge? That was probably our biggest topic this time. So, that's going to be there. So, I would expect those definitions. Is that all right with everybody? Yeah, I did a good job drawing that, John.
It must have been you who put that up there. I can't imagine who else would write that.
That's what I think too.
I wasn't talking about the drawing. The words above it.
The words above it, they're very nice. But anyway,
Don't just give me a hard time.
I'm glad somebody's doing. People being nice. So anyway, let's go ahead and get ready for the final. Let me open up the floor to any questions people have about the test that you just got back. Does anybody want to ask you? Say, how did you do this problem? I didn't get it. What should I have done?
Do you go over part 3?
Part 3. Yes, ma'am, I sure can. Part 3 has to do with showing something tends to minus infinity. So here, number 3 says prove minus 3n plus 2 is in runs from 1 to infinity tends to minus infinity.
And we're supposed to use the definition of what it means to tend to minus.
It's not part of the proof. It's not part of the proof, but I'm going to put it down. What does it mean for a sequence to tend to minus infinity? So recall, x of n tends, as a sequence, tends to infinity, or minus infinity. If for each alpha, there's a real number. So for each real number, for each one of them, there exists a k. So the k depends on whatever alpha is. There exists a k, k element natural numbers, such that for all n bigger than or equal to k, x of n, we're going to minus infinity, is less than alpha. Okay, so no matter what number you give me, there is a spot in the sequence, such that from that spot on, the terms in those spots are less than alpha. That's what it means. Okay, so here's the proof. So it says no matter what alpha you give me, I give 1. Let alpha be given. We need a k element natural numbers, okay, such that for all n bigger than or equal to k, x of n will be less than alpha. What's x of n? It is minus 3n plus 2 will be less than alpha. I don't know what alpha is, just some arbitrary number. So here's what we want. Most of what I want is this. So I'm just going to write it down. That's what I want. I want minus 3n plus 2 to be less than alpha. Okay? I want to make sure that happens. And it happens for all the n's bigger than some number k. Some natural number. Well, let's just concentrate on what we want to have happen in general. So we want solving for n, we want minus 3n to be less than alpha minus 2. So now to get n by itself, we divide both sides by minus 3. So we want n to be greater than, I have to change the direction of the inequality because I'm dividing by minus 3. So we want n to be bigger than this quantity. Well, how do I know there's any natural number bigger than this quantity? There's a big fact that we have. What big fact is that? Yeah, so by the Archimedean property. That's right. So by the Archimedean property, so don't forget we're going to have a study session from 6 to 8 on Sunday. By the Archimedean property, there exists a K, element natural numbers, such that for all, such that K is bigger than this alpha minus 2 divided by minus 3. So I know there's one natural number bigger than K. But wait. If you give me any n bigger than K, well, if n is bigger than K, and K is bigger than this quantity, then n is bigger than K is going to be bigger than this quantity. And for me, that's good enough. But if you wanted to, you could continue. This is good enough for me. You stop here. But you could say, so for all n greater than or equal to K, we have, well, if I multiply both sides by minus 3, so minus 3n is less than alpha minus 2, which implies, so I'm just going to keep on with this prefacing comment, which implies minus 3n plus 2 is less than alpha. And that right there implies that minus 3 times n plus 2 tends to minus infinity. Because I found the K such that beyond that K, the terms of the sequence are less than the alpha that was given to me. Melissa, is that okay? All right. What else would anybody like to see done? Any questions from that test? Any questions? Any more questions? Okay. Well, here's what I want to do, if it's okay. Any questions about anything for the course? Yes. Go ahead, Megan.
On the study guide, you have they'll ask us to prove at least for the following.
Yes.
So do we not have to know the ones from our first study guide?
Say that again.
Do we have to know the proofs from our first study guide?
Okay. So, Megan, I think everything's fair game. But I'm probably just going to ask you for from here.
And Cauchy converting theorem, have we proved that? Like for our study guide on test 2?
No, we did not. Do you want me to do that?
Well, it's probably my notes.
It is in your notes, but I can do it. But, okay. So I understand you're not asking me to. Megan, I want to be a little clearer. Am I going to restrict myself to writing a test that only has these 4 out of these 6? Yes. So if you learn these 6 things, those are the things in terms of proofs of name theorems. Yes, that's what I'm doing.
What about algebraic quality of convergent sequences?
I won't ask you to do that. I might ask you a true-false question about it, but I won't ask you to prove it. Okay. So you wanted me to narrow it down further? That's okay. I will. So what Megan asked was, are our proofs about name theorems only be from that list of 6? And I said yes. Okay. So that's what I said. So if you learn those 6 things, that'd be wonderful. Yes, ma'am?
So, to narrow it down somewhat, you said know all the definitions. Could that be safe to say know all the definitions from the study guide, the first study guide and the second study guide? Just practice all of it?
Yes, and I think that there's a little bit more. So a little bit more, Audra, would include knowing absolute max and min. We covered that for a function. Okay, so what does it mean for a function to be bounded? I don't think that that was listed. We knew what it meant to be bounded on a neighborhood, but not what it meant to be bounded on an interval. Okay, that was the definition that came later. So that's something to look at.
So test 1, test 2, and then the things that we didn't cover in test 2.
Right, that came after. Yeah, those definitely, they're all fair game. I'm not going to narrow those down. But I'm going to ask you for sure, I'm going to ask you major definitions. I might have a few that you'd say, well, I didn't think that's so major. Maybe so, but there'll be a few of those. Because I'm going to ask a lot of definitions. One of the things I think is difficult for this class is there's a lot of content. Do you know what this is? Do you know what this is? Do you know what this definition is? Can you give an example of this? Is this true? Well, there's a lot we cover. Okay, anybody else with anything in terms of questions?
Do you know if you're gonna have a proof for an induction? That's my weakness, I don't like those.
I don't feel comfortable answering the question.
Okay.
It could be there.
That's okay.
It could be there. Induction's part of a proving technique, and it's something that we should be able to do. But let's say this, I'm for sure going to give you 4 out of 6 of these types, okay? And I'm not going to ask you to do any other proof of a name theorem. If I have a problem, can you just show that this statement is true by induction? Okay, I might have that, but I'm not going to commit one way or another. Anybody else? Okay, well, what I'd like to do then is go through some of these proofs. Get some start on the practice. So, let us turn the camera and brace the board, and we'll just do the limit, the squeeze in for limits of functions first.
And we'll look at that Cauchy convergence.
Which we had to quote, I think, did we not? Did we quote that? On test 2? So here's a squeeze theorem, let's recall, squeeze theorem. For function limits. Okay, so Dalvin, I'm a person. I don't remember everything. Megan, I'm a person. Okay? So here's what comes into my mind first. What's the setup for this problem? What's the setup for this theorem, I should say? So it's a squeeze theorem for functions. So function limits. Probably going to have functions involved. It's going to have limits involved. So I know we always start off with a domain. So I'm going to say, let A be a subset of R. F, so there were 3 functions involved. G and H, they go from A into R. And since we're talking about limits of functions, I'm going to have in C, what am I going to say about it? Be a cluster point. Okay. Now suppose that f of x is less than or equal to g of x is less than or equal to h of x. And that's true for all x elements of A except x equal to c. So, yeah. And I should say except possibly x equals c.
It may not even be in the domain.
That's right. Suppose, so I should have put a period here. Suppose the limit as x goes to c of f of x equals to theta sub 1. No, it doesn't say that. It says w. And the limit as x goes to c of h of x, the bigger function, equals to w. Then the conclusion is the limit of the middle function, that is g of x, that is equal to w. Okay, that's the statement. All right, so we want to do the proof. So the proof has the setup assumed, that is, we're going to let A go from A be a subset of all R, F, G, and H go from A to R, and C be a cluster point vector. And then here, suppose f of x is less than or equal to g of x is less than or equal to h of x, and that's true for all x element of A except possibly x equals C. Suppose the limit as x goes to C of f of x equals to w, and the limit as x goes to C of h of x equals to w. Now, I've just rewritten part of the theorem, okay? The hypothesis. We're assuming. This is what we get to work with. Okay? This is what works with us for us to get to conclusion. So we want to show, so I remind myself, what am I trying to do? We want to show the limit as x goes to C of g of x, the middle function, that that's equal to w. So I'm trying to show a limit of a function. It turns out that we can show this limit of the function using the definition, okay, pretty much, of a limit of the function. So I have to go back to that definition. What is that definition? We let epsilon be greater than 0 be given. We want, what do we need? We need, I guess is what I should say. We need, what do we need? What do I need? I'm trying to show a limit of a function. What's involved? Give me an epsilon, we need a delta, that's right. That's right, delta, that's right. All right. We need a delta greater than 0, such that for all x in A, with 0 less than x minus C being less than delta, then we want the absolute value, g of x, that's the function we're talking about, minus delta to be less than epsilon. That's fine.
Are you using W or L's?
Oh, made a mistake.
I'm using W's, I don't know.
No, I'm using W's too. Except what happened for me right there was I got just so accustomed to the definition that I wrote down what the definition said instead of what's involved in our particular problem. So I made a mistake, big mistake. Okay, so this is what we want. All right, well, how are we going to get this? Well, the way we're going to get this is we're going to start working with the facts that we know that f of x and h of x both converge to w. So since the limit as x goes to c, f of x equals to w. I've been given an epsilon already. And so epsilon's been given, I know this is true, so I use the definition of convergence of a limit of a function here. To say that there does exist a delta sub 1. That's a delta sub 1, greater than 0. Such that, you can say delta, but I'm looking for a particular delta. Here's one that works for F. Such that for all x element of A, with 0 less than x minus c less than delta, then the absolute value of f of x minus w is less than epsilon. So, for all x element of A, with 0 less than x minus c less than delta, we have this. we have minus epsilon is less than f of x minus w, which is less than epsilon. Say that again?
Is it still delta sum 1? Or
Yeah, delta sum 1. Yes, ma'am, sure is. Sure is. So, for all x element of A, with 0 less than x minus c less than delta sum 1, here I'm going to solve for f of x. Why? The reason I'm going to solve for f of x is because, remember, if I say something about f of x, it helps me say something about g of x. Why? Because I know f of x is less than g of x. Is that okay? So I want to say something about f of x here. So here, plus w, isn't that right? Less than,
wait, no. Oh, no, that's right.
f of x less than epsilon plus w. That's what we're on. So I'm saying some statement about f of x. Now similarly, since the limit as x goes to c, so the way I think about this is I did all this work for f of x. Now I'm going to do the same thing except for h of x. There exists a delta sub 2 greater than 0 such that for all x in A with 0, 0 being less than x minus c being less than delta, then the absolute value of h of x minus w will be less than epsilon. So this should have been delta sub 2. Delta sub 2 now. I'm going to skip to the punchline of this with the h of x. The punchline of where I want to get to for a statement involving h of x. But the process is the same that I wrote above about f of x. So here's what I want to say. You know what? I'm not going to skip it. I want to skip something. So for all x element A, with 0 less than x minus c less than delta, here's what we have. We have h of x minus w sandwiched in between epsilon and minus epsilon from the previous line. And again, this should have been delta sub 2. So for all x element of A, with absolute value of x minus c being bigger than 0, less than delta 2, we have, I want to say something about h of x. We have minus epsilon plus w is less than h of x, which is less than epsilon plus w. So what I'm going to do is I'm going to let delta, the one I'm looking for, be the minimum of delta sub 1 and delta sub 2. That's what I got, the minimum. All right, with that being the minimum, then as long as we're in A, with 0 less than x minus c less than delta. So if you're less than delta, you're less than both of these things. If you're less than both of these things, we get the punchlines, as I call them, for h and for f. So what we have is, then the punchline for f was f minus epsilon plus w is less than f of x, which is less than epsilon plus w, and minus epsilon is still on this board, you can see it. So minus epsilon plus w is less than h of x, which is less than epsilon plus w. Now look, this 0 being less than absolute value of x minus c says that x is not c. So x isn't c. And what we know is for all values in A, we had that relationship that f of x was less than g of x, which is less than h of x. And so what I say is, for all x element of A with 0 less than x minus c less than delta. The statement I'm about to write is true for everything in A, except possibly C. But I'm just narrowing it down to these x's. Okay? We have f of x is less than g of x, which is less than h of x. And this is true essentially by hypothesis, but I'm narrowing it down just to these guys. Okay? So now, look. So, for all x element of A with 0 less than x minus c less than delta, I'm going to take parts of all three of these inequalities. This one, and this one. Here's what I'm writing. The smallest thing is minus epsilon plus delta. There it is. It's less than f of x. I don't know, right here it is. But what's f of x less than? Well, right here it's less than g of x. Oh yeah, g of x. Which is less than h of x, which is less than, now look, h of x is going to be less than epsilon plus delta.
Is it supposed to be less than or equal to between
That's what I
functions?
was wondering.
Between here, yes, it probably is. So it's probably less than or equal to in the statement. So we need to maybe go back and correct it. This mistake. Yes. Yes, it is less than. Thank you very much. Let's turn the camera. So, for all x in A with 0 less than x plus x minus c is less than delta, the stuff that we have, then cutting through to what we were looking at, just looking at part of it, we have minus epsilon plus delta is less than g of x, because I want to be talking about g of x, which is less than epsilon plus delta. So solving where I just have epsilon or minus epsilon on the far left and epsilon on the far right, here's what I have. So for all x element of A with 0 less than x minus c is less than delta, then here this would say minus epsilon is less than g of x plus delta, which is less than just, not delta, w, which is less than epsilon. So, one more statement. For all x element of A with 0 less than absolute value of x minus c being less than delta, I can take this inequality. This inequality is true, but I can rewrite it as an inequality that involves absolute value. So it says that g of x plus, I think I made a mistake here. It shouldn't be plus. I wasn't paying attention, but I should subtract w from all parts. Big mistake on my part. Is less than epsilon. Okay? So make that change. Well, what does this mean? If it's true for all x's in the domain of the function g of x, with 0 being less than x minus c being less than delta, that g of x minus w is less than epsilon. That's true for any epsilon you give me, that there's this delta. What does that tell me?
And then x goes to c. Equals A.
That's right, and that's what we were looking for. So really, there's a technique involved here that you really apply to both F and H. And once you get those, you let delta be the minimum. So you can be close enough to C. Okay? And then you use the hypothesis that F of x is less than G of x is less than H of x. Work with those three inequalities and get your answer. Is that okay with everybody? Okay. Well, let's try the next one. It's the one that, well, at least we'll get started with it. It's the one that Megan mentioned. was the Cauchy criterion for convergence. Yeah. That's the next one on the study guide.
So the Cauchy convergence theorem, that's what I call it. Another name for it is Cauchy criteria for convergence. Here's what it says.
We had this on the test.
We just got back.
So what it says a sequence X of n converges in R if and only if X of n is Cauchy. That's what it says. That's where we are. That's the statement. Look, if you can get the statement, you're going to get some points. Because I'm just going to ask you to state and prove it. So stating is part of it, okay? If you get this, that's good.
Okay.
Now, here's the proof. Look, in some sense, one way is easy. So we proved earlier that, here we have this direction. We let X of n be convergent. What do we got to do? We got to show that X of n is Cauchy. But we did that previous time. And I'm going to allow you to just quote that. Okay. So this is me saying you don't have to prove all the details here. We proved it in different theory. So by previous theorem,
You said that theorem is because I don't remember.
it's the theorem right, essentially right before it, maybe two theorems before it even. It's a theorem that says if you're convergent, then you are Cauchy. Do you want me to find it in your notes?
No, I just didn't know if it had a name.
It doesn't have a name.
Okay, thank you.
No, that's a good thing to ask about. No, man, it doesn't have a name. By a previous theorem, X of n is convergent. No, it's Cauchy. Nothing to be sorry about. We did this in the previous theorem, and that's when we wrote down the Cauchy criterion for convergence, the Cauchy convergence theorem. We said, hey, we're quoting a different theorem. We've already done part of this. It's okay. It's kind of like in the monotone convergence theorem. Stop for a second. What's the monotone convergence theorem say? It says a monotone sequence converges if and only if it is bounded. And so if you say, well, give me a monotone sequence that converges, we've got to show it's bounded. Well, we've already proven that any convergent sequence is bounded. So we're done with half the monotone convergence theorem. Because it's if and only if statement, we've already proven it in a different setting. So I'm going to allow us just to quote that. That's good enough. All right, so we're going in the opposite direction. What's the opposite direction? So we let X of n be what? Yeah, a Cauchy sequence. What do we got to show about it? We want to show convergence. Okay. So look, I'm a person just like everybody else. All right, how do I show something's convergent? Oh, well, you give me an epsilon. I want to show that there's this K out there such that X of n inside absolute values minus L is less than epsilon for all n bigger than or equal to K. That's what I want to show. What's L? I have no idea. Is that okay? So I got to get L. I got to get a candidate for L. That's what we got to work on. We got to get a candidate for L. Okay? So here's how we get it. I want to use the definition of convergent sequence, but I don't have any idea what it might converge to. So how do I get a candidate? Here's what we do. Well, by a previous fact, you don't have to prove it again, but by a previous fact, since x sub n is Cauchy, then x sub n is, anybody remember? Bounded. All right. Cauchiness implies boundedness. Okay. So if Cauchiness implies boundedness, then we're looking at x of n being bounded. And what do we know about every bounded sequence? Well, it has a convergent subsequence. What's that called? It's the Bolzano-Weierstrass theorem. So by the Bolzano-Weierstrass theorem, there exists a convergent subsequence. You know, I said L, but normally we don't even call it L, we call it X subsequence. So X sub n sub k, k runs from 1 to infinity, that converges to say so it converges, so I'm giving it a name to what it converges to.
Did you say we can put what includes there, or you want to include?
No, I said you could put it. Yeah, I'm trying to be nice, Megan.
Oh,
Yep. Mark it down. I can't be nice. Doesn't have mark. Put it down. Huh. What we're going to do now is we're going to show. X sub n. I know X sub n sub k. I'm going to show X sub n converges. Text. Okay, so I got some candidate for which I can try to show that X sub n converges to. Okay, all right, how are we going to do this? I'm going to use the definition. I'm going to let epsilon be greater than 0 be given. What do I need? Oh yeah, we need a delta. We need,
Nice try.
yeah, right. That's the right reaction. We need a
Okay.
K. Yeah, what the heck is he talking about? We need a K. I'm just about to show you the way. What are you thinking I've been drinking so much Mountain Dew?
Not getting enough sleep. I don't know what I'm talking about.
I'm a national number says that for all n bigger than or equal to k, the absolute value of x sub n minus x is what we call it, is less than epsilon. Epsilon, that's right.
it's usually L right
Yeah, L, X, okay. I've written X. I didn't write down theta sub 2.
Yeah.
I said that earlier, John.
Double prime.
Oh, I didn't say the double prime part. Maybe that's why I didn't.
That's why it's wrong.
Okay, thank you. So, yeah. Okay. So here's what I'm going to do. Note that x sub n minus x is really equal to x sub n minus x sub n sub k plus x sub n sub k minus x. What I'm thinking of x sub n sub k is, it doesn't matter, but it's some term from the subsequence. It doesn't matter, any term from subsequence is true, which is less than or equal to x sub n minus x sub n sub k plus the absolute value of x sub n sub k minus x. Okay, I'm gonna write it down. Give you a second to look at it. Now remember, my whole goal is to show that x of n minus x inside absolute values is less than epsilon. That x of n minus x inside absolute values is small. I can make it small by going far enough along the sequence. But I'm saying, hey, well, x of n minus x inside absolute values is less than this one. So if it isn't the case that I can definitely always show that something bigger than what I want to show is small. But if I can show this is small, then I have it. Well, what do I mean by small? This whole thing right here, this addition, would be less than epsilon. Well, if I want this addition to be less than epsilon, one way to get it is to let the first, is to make the first term be less than epsilon 2, and get the next term to be less than epsilon 2. All right, how can I make this guy be less than epsilon 2? Well, wait a minute. The way I'm going to do this is because of Cauchy. I'm going to be able to control this guy. And how can I control x of n sub k minus x? How can I make that be small? Because I know the x of n sub k's converge to x, so I can make that be small. So Cauchiness controls this guy, convergence of the subsequence controls this guy. And that's what I'm going to use. Okay. Well, since x of n is Cauchy, here's what I'm saying. Well, by definition, what does that mean? That means there exists a J sub 1. I'm going to call it J sub 1. I'm going to call it in terms of J's because we already got K's running around to make the index for the subsequence. I'm just going to call it J's. We got J sub 1, element after number, such that for all n and m bigger than J sub 1, then then x of n minus x of m will be less than epsilon. Over 2. No, you're right. That's what I want. That's what I want. Okay, so I'll say since x of n sub k, k running from 1 to 50, converges to x, then there exists a J sub 2 from the natural numbers, such that for all n bigger than or equal to J sub 2, not n, but rather k, x of n sub k minus x will be less than epsilon. Here's what I'm going to do. I'm going to let j equal to the, what should I write here? Max. That's right, the max. I'm going to push far enough along that both of them maxes. J sub 1 and J sub 2. I'm almost out of time. We'll see if we can finish. Then, we have, let's get just a little bit. We have, for all n greater than or equal to j, the absolute value of x of n minus x of n sub j, so I've written, will be less than epsilon over 2, and the absolute value of x of n sub j minus x will be less than epsilon over 2. So what I'm doing is I'm letting m be, if you will, n sub j in one situation, and I'm, for the Cauchiness, and I'm letting k be j in the other situation. That's what I did. Thus, for all n bigger than or equal to j, this says that the original problem, x of n minus x, which we know to be less than or equal to x of n minus x of n sub j,
plus x sub n sub j minus x, which we know by the triangle inequality is less than or equal to x sub n minus x sub n sub j plus x sub n sub j minus x, but that's going to be less than epsilon over 2 plus epsilon over 2, which equals to epsilon. There's a little bit of maybe details missing here that I'm omitting very quickly as we run out of time. That's the reason I'm not putting it on. But that's the proof, and we'll start there next time. And when's next time? Well, the next time we get a chance to meet, if you'd like, is Sunday at 6. That's right. Okay, thank you very much for your time and patience. That's the class.